Hi, and welcome to the lesson about fault tolerance. Here we are going to see how the fault tolerance is implemented in three different scenarios. In the first scenario, we are going to analyze the strong fault tolerance, meaning that the state will be written to some resilient storage every execution unit. The execution unit, which is in our case a microbatch, since we are working with Apache Spark structured streaming. So the logic for this job is very easy. I'm doing only a sample group by count, and I'm emitting the results to the console. And for the generated data, I'm generating different visits that I'm later, as you can see here, grouping by and counting. That's all. I will just start the Docker container. Here, since there are different, in this demo we have different, I would say, requirements for Docker containers, and that's why you will see different directories, one for Flink, one for Flink Python, one for Docker Kafka, one for Docker Remote with CLDB. So that's the reason this organization is a little bit different than in other demos. So I will just go to the Docker Kafka, and I will start Docker containers. Now I will run the data generator. Okay, the topics are created, and let's move on with our consumer, stateful consumer. Okay, we already have the first counts. Let's make it run for several micro batches. Okay, maybe I can just stop here. I will stop the generator, and let's check the checkpoint location, and I will explain to you why this fault tolerance has a strong guarantee. I can already stop this one. We can go to this, and now if you take a tree for all parts, you can see that the numbers in commits, offsets, and state always match, meaning that we have 10 commits and 10 state files. So here the difference is the numbers, because here is the number of the microbatch, currently processed microbatch, and here is the number of the microbatch that will load the state. So the microbatch number 1 will take the state generated for the microbatch number 0. So there's a small difference between numbers, but typically you get the same number of states and metadata checkpoint files on both sides. And it's strong because you can see that whenever we commit something whenever we consider the microbatch as a successful part, we always retrieve a corresponding state file in the given shuffle partition. So the story is different for Apache Flink. So in Flink it's different because when you check the configuration of the checkpoint, you can see that it's time-based. There is no such a concept as an execution unit like microbatch. It's mostly time-based, and additionally you have to enable the externalized checkpoints, because that way you will be able to restart your job after stopping it. Otherwise the checkpoint is only local. It's only local to the job instance, and it will not persist as in the case of Apache Spark. And there's another difference is the delivery guarantee. The delivery guarantee that is tied to the checkpoint location, and you will see that if we run this job for the at least once delivery, we will get more data in the sink, whereas if you run it as an exactly once, you will get the data emitted only when the checkpoint is taken. And that's the place where I will use the different Docker container. Just the Docker container for Docker Flink, where I'm defining, of course, Kafka Zookeeper for the input and the output, and also job and task managers that are the unit of that are the resources running the jobs on the cluster. So I will now edit. So I will now edit this just to be sure that I have the correct job ID, the correct checkpoint location, and good delivery mode configured. Okay, and everything is fine now. So let me start now the Docker containers and the data generator just after. So it's creating the topics. Let me trigger the data consumer also. We should have some partial results emitted. And I will also go to the console and wait for the checkpoint to be completed. At least the first checkpoint, that will allow some time after to show you that this recovery is about at least once. So the checkpoint was completed a few time ago. I will cancel the job. I will also remember all the results here in a separate file. I will stop everything here in this part. Additionally, I will read the checkpoints here, and I can see that I have the chunk 1 to restore. I will now modify the command. So the command is almost the same, except that it has this save point flag that would say that for this specific job I would like to recover the state from this checkpoint location. So now I will start the job, but without destroying the volumes, and of course I will restart my consumer just to see if I have at least once, so if I have some duplicated data somewhere. And you can see that this is the part for the first run, and you can see already a few duplicated entries. So I will just maybe keep it like that. You can see that due to this at least once delivery semantic, some of the records are duplicated. So we can say that this delivery guarantee is a little bit weaker, because depending on which trade-off you make, if you want to have a job with low latency, of course you will configure this checkpoint as at a higher value, and you will have much more state to regenerate, and you might have to deal with duplicates in that case if your data generation logic is not idempotent. And that's for the at least once delivery. So just let me remove all this. I will stop the containers, consumer. I will remove all the data that is stored in the volumes, so keeper and in the checkpoints. And now I will make this delivery guarantee a little bit stronger. I will put it to exactly once. So I have the same configuration, just a different job ID to not mess up with something that could be left after my previous run. And here you will see that we will not have this, I would say, duplicate phenomena. So now I will do the operation for the exactly once. Do I have the command here? Yes, I have the good command. And I will just change the job ID and start it as previously. So I already cleaned all the volumes before. I'm restarting the job. I will start the data generator. And I will also start the consumer, but this time I will define the isolation level as read committed, so that the consumer will only see the results when the transaction is committed. So just this this error. And what checkpoints we have? We have one checkpoint completed. And we have our data written. So now it's time for the second. That was triggered and completed. We're waiting for the third one. So you can still see the partial results here, but these partial results are only visible to when the transaction is fully committed. So yeah, here we already have the third transaction, and I can stop the job. You can already see that we have 3 chunks, so I will not read anything more, so just stop it. And I will change now the command to run, and I will include the last checkpoint location. So it was the chunk number 3, just to remember. Okay, and what about restarting it without the Docker Compose? Okay, now I have data consumed after the restart, and do I have some duplicate in there? You can see that so far I don't have any duplicated values, so it's always one record that exists. I have 22 visits, right, but it's for a different window, so it's not a duplicate. Here it's still one, so I can move on like that, but generally this exactly once delivery guarantee is provided with the checkpoint. So whenever we take a checkpoint, we make the data visible. Whenever something fails between the previous and the next checkpoint, the data remains hidden. The data is not committed, and since we defined the visibility to read committed, obviously the consumers will not be able to see this data. It will be some kind of pending data that will never get promoted to the final output because of the transaction that just failed. So that was for the weaker guarantee, because you can see that with the at least delivery semantic, it can really introduce some duplicates in your data store. The duplicates that you can deduplicate downstream if you have some idempotency logic, or if you have some idempotent ID. Okay, that was for the state stores implemented with a data processing framework, and now I will show you the state store that is provided. Oh, sorry, just stop it. And now I will show the remote state store. So the state store that is provided by a secondary storage, that will be ScyllaDB in my case. So I think that you are already familiar with the code. I will skip the explanation, but just focus on a different element than in the previous demo. So here the location is in ScyllaDB, Docker remote with ScyllaDB, and I will start the database, and okay, that's not a good one. And I will initialize the key space with all the tables. I think you already remember from the lesson about state stores, so I will not repeat myself here. Okay, ScyllaDB is not ready yet. It should be fine. Yes, that's good. And in this demo I will focus on fault tolerance. So I will start data generator and later simulate a failure. So a failure that will recover the state from this kind of backup storage, but in fact this backup storage is our main data store. So that's the main difference between this and the other approaches, where the main data store is this in-memory location, and it's only a fault tolerance is only backup for fault tolerance. Here we are considering ScyllaDB as the main data store, so something that can be even public, even shared with other applications. And yeah, we are processing now all the states here, 333, 334. I can also start another customer just to show you that it can rebalance very easily. But it's, as I said, it's the same code base like for the demo of the lesson number 3, so you shouldn't be lost here. We have processing the data from A, from the last point, loaded, added. That's fine. So now I'm stopping the second customer. I'm stopping the first customer. The data is continuously produced by our producer, but unfortunately in that case our customers failed. And since we have this state which is located outside our customer, so the state is not, it doesn't share the same life cycle of our customers, meaning that this is not dead when the customers are down. We can simply recover the state, so remember numbers 10, 10 and 9 for letter number A, and we will restart the counters from that place. So under the hood it's kind of the same mechanism, so we have data written in a different place, but it's more adapted to some custom storages. So you can see that we correctly retrieve the state number A, and later we also reprocessed the state number B. So in this demo you saw 3 different fault tolerance strategies. First strategy, which is kind of strong fault tolerance, which is tied to the unit of execution like a microbatch. The second strategy that is a little bit weaker because it's configured on time, so you might have some misses or duplicates, as you saw with this strategy configured in the at-least mode. But if you configure it in the exactly ones and you rely on the transactional capabilities of your sinks, you can transform this weak guarantee into a strong one. And the third guarantee, which is a remote, because your state store is not local to the job, is outside the customer, even though there is still this in-memory cache for faster access, but the main storage is in a dedicated database. And here the fault tolerance comes natively with this database because it's provided with all its capabilities, like for example backups or geo-replication for much more alive status. Thanks for watching and see you in the next lesson.